Today we are in the 8th lecture of the systems engineering course, and today's lecture title is Systems Viewpoint, and I am Dr. Deepak Philip from IIT Kanpur. And we need to go through the systems viewpoint today because it's also a recap of what we have done so far, and also it is a precursor before introducing you guys to the different tools of systems engineering. So today's learning objectives involve the major following points. The systems engineering viewpoint is what we will discuss as the first thing. Then we will also talk about the need of balance, or why balance is an important activity of the systems engineering. We will discuss about the domains of systems engineering, and then the various fields in systems engineering. Then we will see what type of approaches we follow in systems engineering and some of the activities of systems engineering. And we will try to combine all of these into the systems lifecycle model. So today, first let's talk about the systems engineering viewpoint. So the central objective is of the systems engineering viewpoint is to treat the system as a whole, and to have and focus on the success of the mission. So it is actually making, if you write about this, it is making the central objective, the system. So the system is the central objective, and you treat the system as a whole. Let's put it this also. You treat the system as a whole, and you are only focusing on the success of the mission. Success is equal to the success of the system. Okay. So you are focusing on the system as a whole, and as well as you are focusing on the success of the mission the system is supposed to perform. And you also require, this is the requirement, is that individual goals and attributes, we have a less than sign. Okay, they always take a lower priority compared to the overall system goals. So in a better way to say is that individual goals and attributes, these kind of things, are subordinated. We can think about it this way: are subordinated, or take lower precedence, or take much lower precedence when compared with the overall system goals, overall goals of the system, or system goals. So what we are saying is that the systems engineer, the systems engineer should always have an overall viewpoint where he or she should be able to look into the overall goals of the system, and then subordinate any individual or goals or attributes to a much lower precedence. And the advocacy of the systems engineer, or the system engineer, always advocates for the total system goals against that of the individual goals. So as I said earlier, individual goals / attributes are subordinated with respect to the system goals. These are the overall system goals. All right. So there are three types of systems that we can talk about in systems engineering, and the one that most of the people commonly talk about is a successful system. Okay, and successful system, I would like to define it this way: it's a system that meets its requirements, and developmental objectives. And it also accomplishes successful field operations, and in the same time maintain what? Maintain a long and useful life. So a successful system is the one that meets its requirements, whatever the requirements of the system, and also the objectives, why the system was developed, the developmental objectives. Both of them, the requirements and the developmental objectives, are met successfully, and it also is able to do successful field operations. When you field the system, it achieves all these objectives successfully, and it maintain a long and useful life. So, the system has a longevity. So, the systems, so in a way systems engineering viewpoint encompass all the three. Three means what? The meeting the requirements and objectives, successful field operations, this is 2, and maintain a long and useful life, that is the 3, right. So, the so how do you develop a successful system? To develop a successful system or a successful system development, successful system development requires the usage of consistent, well documented, well understood, let us not talk documented, let us talk about well understood systems engineering approach within any organization. So, a successful system will meet its requirements and developmental objectives, it will conduct successful field operations, and it will have a long and useful life, and all the 3 are encompassed. And to do this, to develop a successful system, you require the usage of a consistent, well understood systems engineering approach within any organization. Then we talk about another term which is quite important, which is called as the best systems. So, the best system is it's a confusing term, but we need to understand this, because many a times in normal usages in any organizations, the term best systems comes into picture. So, before doing this, let us see what systems engineering seeks. The systems engineering seeks the best possible system. This is the important phrase. We are not seeking the best system, we are seeking the best possible system, which is usually not the one that is the best performing system, or that is the one that is the one that gives best performance. So, we should not ever confuse best performance with that of the best system, because the performance is only one. We can say that performance is only one of the critical attributes. There are many other critical attributes. Some of the other critical attributes are affordability, it should be timely availability to the end user. We talk about maintainability, we talk about meeting scheduled deadlines, all right. So, these things are also critical attributes. So, performance is just one attribute. So, sometimes what happens is that there is a usual saying that people sometimes say like this: systems engineering is the art of the good enough. People do make this statement, but you should not really get confused with this statement, because it is not just you are making compromising. So, systems engineering is not equal to compromising, but it is about deciding the best possible system, not just the best performing system, but the best possible system. So, You cannot say that the system, you cannot compromise the endurance of a system. If you are making a UAV, you cannot compromise endurance of the system for speed, or you cannot compromise the range of the system for endurance or something like that. So, you would like to have a balance, or you try to create a system which will fulfill almost all the critical attributes that are part of the system. And as I said earlier, some of the critical attributes are listed right here. So, then we already use this term, it is called a balanced system, I suggested earlier. But there is also, before we get into this balanced system, we need to understand one concept which is also called as the law of diminishing returns. Diminishing returns. I would recommend you guys to read this, but the law kind of, if you represent it in a pictorial graph, it kind of looks something like this. You have a, in the x axis you have cost, and the y axis you have performance, and then you have some place where the cost begins, let us say CO as the initial cost, and let us say this is the performance, it is 100% is the performance here, this is 100 or the best possible performance, and the system would kind of do something like this. And somewhere here is, you can think about is the system, there will be a minimum acceptable system, and somewhere you will have something called as a, call it as a desired system. Think about this. This could be, let us say for example, it could be a 65% or this could be 85%. The cost necessary to move from an desired system all the way to the best possible system is quite high compared to moving from a, what you call as an acceptable system to a, you can see this is the movement from an acceptable to a desired system, whereas this is the from the desired to the, what you call as the best performance system. So, this law of diminishing returns means that as you keep on putting in the time, money taken to, or the resources necessary to make the best possible system is in return the performance that you derive from the system, it is quite significantly less for the amount of money that you put it in. So, the idea here is that the balanced system, it is the essential function of, so the essential function of systems engineering of SE is to bring or strike a balance, bring a balance or strike a balance among various system components. So, when we say this, when we say we have to strike a balance, what does it mean? So, the idea is that each system components are built by engineering specialists or experts. So, the components are built by engineering specialists. So, when they specialize is, what do they want to do? Each specialist would like to build the optimal component. The person would like to keep on improving it and making it that's the best possible component in the world. But what do SE need to do? The systems engineer, the job is to guide the development. SE guides the development so that each component, each system component receives the proper balance, receives the proper balanced resources and attention to achieve desired capabilities. So, the systems engineer is the one where the engineering specialist would like to build the optimal component, the systems engineer would like to build the balanced component, or he would like to build a component in such a way that where resources and attention is balanced, so that the component will achieve what the desired capabilities are, but without compromising on some other stuff. So, an example, as I said earlier, is that we talked about UAV as an example, UAV as a system where we said one component was airframe, another component was propulsion, one would be communication, another was payload, and one was control. So, among these 5, the aerospace engineer would like to build the best, most efficient airframe, and he would like to put as much as focus onto this. The mechanical engineer would like to build the most fuel efficient, most silent, longest endurance, best operating propulsion system in the world. The communication guy would like to build a communication system that would probably communicate all the way through Pluto or whatever it is. So, the idea is that everybody would like to build the best. So, they want to build the best communication, they want to build the best propulsion, they want to build the best airframe, they want to build the best payload, they want to do the best control systems. And the systems engineer job is to actually say, okay, I understand your drive, but what I want is a balanced system. So, at some point of time, the systems engineer tells the aerospace engineer, okay, this airframe design is good enough. It is the best possible design for achieving the goals, because somewhere in this somebody has said, I want a UAV that can fly up to 70-kilometer range, maybe 5,000 feet altitude, then 10-hour endurance, something like this. So, the systems engineer tries to develop a system that meets these needs or the requirements that are established earlier, whereas the individual engineering specialist would like to build the best possible system. And another way to look at this balanced viewpoint is we can look at it in a graphical view of balanced viewpoint. I would like to use a graph to represent this. So, if you think about it as a 3-dimensional graph, if you have 3 axes like this, assume these are 3 different axes. Okay. This axis, the axis that is going downwards, is denoting technological depth. Here we are talking about the technological breadth, and here we are talking about, let us say, management expertise. So, the specialist, if the person is more into a technological depth, if the person is a specialist in technology, then the person would focus more on a component design. So, you can think about it as a person in a technological depth alone would focus more on a component design. A person who is on a technological breadth might be looking at developing what you call as alternatives or different designs. This would be something that somebody might be looking at who has a wide broad idea of technology. The person who is more into a management expertise or something might be talking about a project management or something like this. That might be the focus of that person. But when you, a systems engineer who is supposed to have a balance among all the 3, okay, so this is where the systems engineer comes into picture, an effort from all the 3 different axes. Okay, he balances all the 3, and so for that purpose, SE is required or expected to have significant knowledge in all 3. Which are the 3 things? 3 things are technological breadth, technological depth, and management expertise. So, here is an example. This credit of this diagram goes to Rick Hendricks, and it was published by Catherine Dax in an article. So, if you talk about, let us take an example as a wind turbine dream machines by different experts. So, here the wind turbine is being visualized by the, if you think about the aerodynamics guy, he literally focuses on making this the most efficient system which would actually be able to work in the slightest wind conditions possible. If you talk to the guy who is on the acoustics, who would be more interested in designing it in such a way that it produces the minimal sound. The person who is in the control systems or who is more into the control system, this is the way he might envision the windmill. And the person who is on the grid, he is like, I don't care how it looks like, but I want the maximum electricity out of it. The person who is doing the manufacturing, how cheapest I can make. So this is the manufacturing view of it. The service person is like, can I make it in such a way that I don't need to do anything to service it, or the minimum serviceability. The person who want to make it this as part of the weight, or the structure guy, or the person who is thinking about reducing the weight or optimizing the weight, he might create a system like this where say, okay, fine, let the blades be made of paper. And the structure guy is like, okay, I want to ensure it in such a way that it will not fall even if the entire earth rips apart into 2 or 3 pieces. So what I am trying to say is that every expert has its own viewpoint. The aim of the structural engineer, the systems engineer, is to get input from the aerodynamics person, the acoustics person, the person who is managing the grid, the manufacturer, the service guy, the controls guy, structure guy and weight guy, and all of these he would like to integrate and create what we call as a balanced system. The inputs are vital, but what to take and what not to take is the aspect of the systems engineer. I think this diagram, when again credit goes to Rick Hendricks, he is the one who actually came up with this good diagram, which gets the point across how the systems engineer strikes a balance among a bunch of experts. So we now talk about the balance viewpoint, and the balance viewpoint is very simple. It basically says this: no system attributes grows at the expense of an equally important or more important attribute. So a systems engineer should ensure that no system attribute gains undue importance. So here is that no attribute gains undue importance. So the systems engineer ensures that if an attribute, because what happens is if you put undue attention to one of the attributes, then it will impact the some other equally important attribute, because the total money available is constant. So the consumption here is funds available for the exercise of system development is usually constant. So this is an important aspect. So you don't have infinite sources of funds. So then the idea is that you have to ensure that sufficient or enough attention is given to all attributes, and nobody gets an undue attention, or no attribute get an undue attention. And other aspect is, this is kind of a truth, most of the critical attributes are interdependent. So I said earlier, some of the critical attributes being maintainability, obviously performance is another one, then usability, longevity, reliability. So many of those kind of things, the many of utilities is part of this process. So all these ones are interdependent. So if you tweak one, somebody else will get tweaked in a way that you did not expect or did not want. So as I said earlier, all these attributes being interdependent, so that's where no system attribute grows at the expense of another equally important attribute. So hence the systems engineer balance between the technical depth, technical breadth, and the management expertise. You remember the previous diagram that we drew like this: the technical breadth, the depth, and the management, and the systems engineer's job is to strike the balance among all the three. So now from here we will jump into the systems engineering domains. Okay. So the domains are like, one is engineering, obviously. So engineering, you can think about it is converting available knowledge to product slash service. For the time being, let us assume engineering to be something like this. So, here is where the things actually get made. Okay. Then there is also the technical domain. Sometimes what for example is we consider sometimes whether a new material is to be developed, can technology or can current technology satisfy the requirements. So, can we build a system with the current technology that will fulfill its needs or demands? So, that question comes from the technical side, that question gets answered. Sometimes new technology that need to be developed, that all aspects comes as part of it. The social aspect to a large extent is the social, human, political, legal management, these kind of things that many people sometimes call as the soft side of systems engineering. Are they really required? And yes, this is required because these are necessary to fully understand the impact and utility of the system, and its development in a global scenario. A classic example of this is that if you think about the aerospace industry or the aircraft industry, aircraft manufacturing, if you look at the histories of the companies like Boeing or Airbus or EADS, we can see that initially they focused us more towards the developing aircrafts which are important to their locality, like the Boeing was focused more on the Americas continent, whereas the Airbus was focused more on the European, because that is where the air travel originated and flourished. But pretty soon, as the global market opened up, other continents need to be connected and people started moving from continents to continents and other stuff. Then the market became global. When the market grew outside this, these companies actually started looking into the different aspects of it. Like for example, some of the design of aisle space or the leg space or usage of anthropometric data. All these things were done as part of the social, human and other aspects of the design, the soft side of the design being added into the system. So, this provided the airline agencies or airlines to customize their aircraft to the needs, to the population that they survive or serve. Now, we also talk about the systems engineering fields. So, there is the engineering field, then there is the modeling, simulation, control systems, architecture, quality. These are the major engineering fields. So, if I represent them on a diagram, let us think about this first bubble as the systems engineering bubble. Let us think about this bubble as the management bubble, and let us think about this bubble as the engineering bubble. Then some of the tools that we talk about it is, like for example, architecture is something like this. Architecture will be systems engineering and an engineering bubble contribution. There you are doing the product architecture or process architecture or something like that. Similarly, another one would be control systems. This will be quite a lot into an engineering domain as such. You could also even think about something like a quality as part of this. How do you produce a quality product and stuff like that. But somewhere in the whole ambit of the things, you might have a bubble something like this, which we can call it as a modeling and simulation. So, some aspects of management like simulation or modeling of the production systems or something like that, or simulation of a manufacturing system. Similarly, in engineering there is something called as a colorful or the CFD, which we call as computational fluid dynamics. Sorry, it is a tongue slip. I usually make fun of it as colorful fluid dynamics. But anyway, all the said and done, the CFD is another example of a simulation that is being done as part of engineering. In management, we again have things like management and systems engineering. We have HR or human resources. We have some stuff called OR, operation research, which is again part of systems engineering and management. I draw the bubble wrong. Then more into management and systems engineering is the project management. So, there are different fields in engineering or the management which shares common boundary between the systems engineering and one of the either management or engineering. So, what I am trying to say is that these fields, it might be important for people to be experts in certain fields, but systems engineer should strive towards obtaining working knowledge. I am using the term working knowledge in quotations because in the associated fields. This is important in this case. So, while there are wide varieties and there are experts available, the systems engineer should know when the expert says something what he or she means. He might not know the nitty-gritty details, but he should have sufficient capability to understand what that whole discussion is all about. Then we talk about certain the activities and documents of the systems engineering. So, the user needs understanding and documenting is one of the activity. Understanding and documenting. Developing the scenarios where the system will use. So, development of them and making them into a document. Developing use case. Okay. So, this is where the ConOps concept of operations will actually get linked with of. So, it's the development of the use cases. You look at opportunity assessment. So, like where all the systems can apply, systems can be used. Okay. What are the other opportunities that is available as part of the system development? The functions, the documentation of the system functions, the design and choices of component interfaces is one part of it. We already seen how we do documentations for trade studies as part of this, because this helps in the PBS, the product breakdown structure. We already talked about this. How do we integrate prototypes, and how do we develop a production and operations plan when the development plan is translated to manufacturing or production plan, something like this. Verification, validation, and then there are other aspects also called context diagrams. Then there are other aspects called the problem definitions. Then we have disposal / reuse plans. How do we develop those kind of things? How do we dispose the product? Or do we have an upgrade, revise plans? This is another aspect of it. Then we have a field support and a maintenance document. Okay. We also have the prototype testing and evaluation. We also have the component development and test. Like this, we have quite a lot of documents that are available. There are stuff like the traceability that we already talked about. Traceability. There is stuff like the technology readiness, etc. So, there is innumerable number of activities and documents that are done as part of the systems engineering, and this is necessary because this is where the entire document of how this complex system, has been developed, and it is required because it will also serve as the knowledge base for the future activities to come. So, with this what we will try to do is we will try to actually we study the systems life cycle and why life cycle of a product is important. So, we will try to see whether the to capture the entire system life cycle and its critical aspects using block diagrams, so that we can review what we have done so far before we jump into specific aspects and tools of systems engineering. So, the initial part, as we said earlier, if you draw it as a block diagram, the first thing that we are going to do is the need analysis. We talked about this, what it is. Further details will be available to us in the future slides, but the one of the things that actually comes into this is the market pull, okay, the information. Then there is something else that is called as the technology push. Like for example is, why would countries keep on building a third generation fighter, fourth generation fighter, fifth generation fighter, keep on upgrading the fighter? Because that's where the technology push comes into picture. Newer technology means newer capabilities, additional capabilities, better rate of success and stuff like that. And similarly, there might be a need for you might be in the product business of building and selling aircraft. So then there might be a market pull. The people who are buying the aircraft might be looking for a better product. So you need to keep on upgrading the product. So the one major aspect of all of this is the customer requirements or customer needs / requirements. So the need analysis from here, it is developed, and then it moves into the next stuff, which we kind of make another square, which we called as concept exploration. So from here, from the need analysis to concept explorations, we will have discussions, we will have collaborations, we will have brainstorming, etc. Okay. And in this case, the major thing that will happen is the market assessment happen. The market assessment, then the system and product concept definitions, system, product, concept, definitions. We also have the this will be preliminary. Okay. So we have developed a concept. We are exploring the concepts. What are the possible options? What are the possible concepts that the system is capable of, or what are the possible configurations or concepts that can be explored to realize the system. And from there, we basically get into the definition. So the third will be concept and program definitions. Concept and program definitions. So you have gone through a lot of explorations. From here, now you are defining things. So this is where the idea of planning comes into picture, where you have pricing or estimating. Here you are deciding how much it is going to cost. We do the proposed product definition. We also do the functional or the system block diagrams. Okay. So all of these things are done as part of the concept and the program definition. So the planning of how to execute the system. So from the exploration you are narrowed down. So here it is the narrow down. You are bringing it down to a concept that you think it is feasible, and the detailed aspects of it is being created. From here we get into the next one, next box, as we call it. We call it as the, let's call it as the contracting and project management box. Okay, in this what happens is the project office or the start the work gets established, then the WBS or work based schedule, or the how the work gets divided, that gets done. Risk assessment plans gets built at this point. What's the risk that we pose this? The budget and schedules. So here we ended up making the how much of the pricing, the estimating of this. Here detailed budgets and schedule gets built. Then you also get some making the PERT and the Gantt charts, against which the development will work forward. And then from there we move to the next bubble, or the next box, where we actually do is the information that flows is specs, or the specifications, plus the design, the tentative design flows from the contracting and the project management. So at this point you are identified, somewhere identified who will do the work. This question has been identified to some level here. So in the second step, once this is done, then we do the next phase, which is called as design / technology validation plus engineering development. So in this, the major activities that we do is the work orders and authorizations. Then we have the critical path analysis, which are the critical activities that needs more focus. Then you do a prototype development. You also have the PDR, which is called as the preliminary design review. Then we also have something called as a evaluate prototype. It's also called as the beta testing. Okay. So all these aspects are part of the engineering, the design and technology validation plus the engineering development. From here we move to the next step. So you can see that we started with the need analysis with the components of it, then concept exploration. You are exploring widely what are the options available. From there you narrow it to concept and program definition. From there you do the contracting and project management. Then you move to design and technology validation plus engineering development. From there we get into the next part, the next bubble, which does something called critical design review, or CDR. This is done and it goes into another big box, and let's call this big box as production or manufacturing. You can also call it as development of the system. Here the aim is that you do fabrication of subsystems. So the prototype has been designed and agreed, and the critical design review said, okay, let's go ahead and make it. So the subsystems are being fabricated, the large scale production, so that the same uniform products gets produced. System integration, the subsystems that are produced get integrated. Then you do verification to ensure that the integrations is correct. Then you do system test and evaluation. So here you are doing the large scale production. So here to a large extent you are ensuring that the repeated production happens. Repeated production of what? The desired system happens. All right. From there we move to the next box, which does the delivery plus install. So this box, what we call this as the testing and evaluation plus operational support. Here you do the testing, and this is mostly like in the field test, not the product testing. So, you are taking the product into the operational area and then doing the field testing and evaluating. Then you also do operational maintenance as also so part of this, and we also do what we call as the quality checks and supports as a part of that as well. From here we get into the next bubble, which we call as the last bubble, where now the system is in a place where it is operating and all. So, this is the system use bubble or the rectangle, where what we decide stuff like close out, okay, or should we do a follow up of this, continue to develop further. So, here the major important things are the logistics and warehousing. So, here the system is operational, you are supporting it. So, here you have your spares and other aspects as part of it. Okay. So, after some point of time you decided that okay fine, the system is not doing as well as it is expected, there are better systems available. So, shall we close out it, shall we shut down the development, or the system is doing extremely well, can we continue to develop a further different versions of it, all those aspects gets done out of it. So, from the previous slide started with the technology push and the market pull, which started the need analysis all the way to the system use, where we decide the close out or the follow up, is a graphical, you can kind of call it as a flowchart view of the system life cycle. And there are tools, this whole life cycle is controlled oversight by the systems engineering, and there are different tools and techniques available at each stages to make the appropriate decision. We will now start seeing these tools, and so the next lecture will be on the system building blocks, and after that we will get into different tools and the aspects of the systems engineering. Thank you very much for your patient listening.